Hi guys, I'm Funman, and today I'm demonstrating a quick guide on the use of MestreNova, the NMR analysis software that you will use in the lab. When you receive your NMR data from a TA, it will be in the form of a zip file. So the first thing you have to do is, you have to unzip the folder and convert it into a normal folder. Use WinZip to unzip the file and download it to the local drive. Once you have unzipped the folder, you have a folder with all the NMR files inside. Now open the MestreNova software, which is in the version 11. Now in this version, there are two ways of opening up your NMR file. The first way is very simple. You're just going to drag using a mouse the folder of your NMR data into the white blank space in the software. And now you see immediately that the file will appear. The second way is to, using the right empirical way, clicking the icon, File, and Open, and go to your NMR data folder, and select the file that's named FID, FID. You see, it works perfectly as well. Now one of the advantages of MestreNova software is that we can open multiple data. We can open multiple windows so that we can process multiple data at the same time. Now to familiarize the program, you ought to know all the toolbars and icons they represent. So above, you see there are many toolbars. Let me introduce to you bit by bit. On the top here where my cursor is being placed, we have a zoom in function. There's a shortcut where you can now hold your mouse cursor and drag to the area that you like to zoom in larger. So you can zone in and focus more to see it more clearly. Now let's say you're done and you like to look at the full spectrum. You just click on this icon and you have it zoom out. And the zoom out function is here, just next to it. Now there's this icon called the manual zoom, and this is where you can key in the exact chemical shift that you would like to localize and see it larger. So you type the chemical shift in ppm and click OK. So in this case, I demonstrate using from 8.0 to 10.0 ppm, and voila, you see it zoom in to that region I want to. So is it a triplet or a quartet? When you zoom in, you know. So again, let's zoom out. What do we click? The full spectrum. This icon I'm pointing to is the expansion window, and this is where you can zoom in and place a smaller snapshot of what you are trying to magnify. You see how beautiful! A snapshot inside a presentation. And the next important icon is the PDF file, and this allows you to convert your file into the PDF format for submission. The left click on your mouse is to select the window and the particular object that you like to move. So we have the big one, there's a whole spectrum, and the small snapshot. So I accidentally pressed delete and it's all gone, but fret not, because if you do anything wrong, just press Control and hold with Z. Okay, you just back undo and you get back everything. How lovely. So now let's select the small window and delete it from here. And now let's look back at the full spectrum. So the height of the NMR signals could be adjusted by scrolling the mouse, the scrolls. If you roll it forward and roll it backward, it will shift. So play around with it and see which height you would like to have. You can adjust the height of this signal, depends on the purpose you want. Like for instance, if you want to have more snapshot of the different regions in your NMR spectra, you might want to lower the height of the main spectrum so that it doesn't block it. If you do a right click, you see the menu, it says Cut, Copy, Paste, Delete, Select All, and Properties. Now the property option is very important. Now let's click it and see what we have. Here you see many parameters you can select and change. And next, whether you would like to have a grid line or not. Next is your scale. For the chemical shift, what range of the chemical shift you would like to showcase. And for the vertical axis, it is arbitrary. So we normally uncheck the box for vertical axis. And later on, we're going to talk about the peak manipulation and Pigpicking. So now with grid, this is how it looks like. Maybe more beautiful to you or not. Okay, you see horizontal and vertical grid lines. Again, we go back to the properties and let's uncheck the show horizontal and show vertical lines. And for now, if you have the horizontal and you do the vertical, right, this is what you see, something like that. Okay, you see the right hand side, you show the axis. It is really not necessary because it's arbitrary, and for the y-axis, it's not important to us. So we uncheck this option and click apply. Okay, so the first step to do NMR analysis is to go to the processing option and do the phase correction. And here we should do it automatically. Click automatic. Okay, and now it gives you a very good baseline. There are 3 essential key steps in the processing of a one-dimensional proton NMR. The first is to conduct a reference to calibrate your NMR spectrum. The second step is to do the Pigpicking to select the chemical shift of the signal that we are interested in. And the third step is to do the integration of the signals to see the ratio in the relative environment of the protons. So now the first step, we do a reference using the solvent that we use to dissolve our sample. So typically the mode of the NMR will run in CDCl3, the deuterated trichloromethane. Now in CDCl3 there's some residual CHCl3, and we can see the signal. Let's zoom in, and this signal will be at 7.26 ppm, parts per million. So let's use the cursor to zoom in, and we can use the Chcl3 Peak to zoom in and to calibrate it. So all the rest of the signal will move according to this, and it's all consistent. So now let's zoom in the area at about 7.26, and you see this distinct single peak, and that must belong to CHCl3. Now let's go to the option Analysis, click Reference and Reference again, and click. You see, you put the cursor over, there's a red line, hover it, you click, and there's old shift and there's a new shift. So you can key in, type 7260 ppm, and we click OK. So now the whole graph, the whole entity will shift according to this relative signal, our solvent peak. So after calibration, what we are interested to do is to do the Pigpicking of the peaks signals that we are interested in. So next again, we go to the icon Analysis, Pigpicking. We could do an automatic Pigpicking or the manual one, but now let's try the automatic one. But the thing is, using automatic function, the machine is trying to pick up so many peaks that it's very messy and it doesn't look good. So try not to use this function for our purpose. We will be accurate because we can predict what product we're going to have in our reaction. So let's go back again, Analysis, Pigpicking, and we do the manual threshold so that we can isolate and identify the signal we really want to analyze. Okay, so we place the cursor, we click and hold to the signal we like to investigate, and click, hold it, and drop on the right. You see this area, and then you see at the top there, it shows up, right? It shows the chemical shift of these two signals, the doublet. And here, this is the multiplet. We can again do the same thing and drop your mouse cursor, hold it, left click, hold it, and shift to the right, the region, and let go. So now we see that there are a few minor impurities located at this portion, right, and do not want them to be inside our analysis. So sometimes we are not interested in these signals, we do not have to care about them. Now another thing is, we did the reference, so the singular peak for the CHCl3 is being shown as 7.26 ppm, exactly what we wanted. Now for the chemical shift, we might wish to have more than 2 decimal places for the value to calculate the coupling constant. So we do a right click, go to properties, and we go to peaks, and here we have the label. It is checked right now, and at the bottom it says here decimals. So right now it's at 2, we can change it to 4. We click apply, and now we see 4 decimal places. So this way we can accurately calculate the coupling constants. So now you see the curve, the portion here that's labeled in green. The program automatically integrated some part of the signals that we do not like to see. So what we could do now is to go back to the properties and click onto the icon, curve, and uncheck the peaks and residual and click apply. So now you see these green color regions are gone. So now we do a cleanup, we only see the chemical shift and the spectrum that we want to have. Click OK to exit. And now the next step, we have to decide how many hydrogens per signal represent, which means the integration ratio of the signals. The compound right now we have here in this example is your trans-cinnamaldehyde, and let's take a look at the structure using ChemDraw. Now by now you should know how to use the ChemDraw and draw your molecules. So now this is the structure of trans-cinnamaldehyde, and for MestreNova it's very good because it is in sync with ChemDraw. You can just drag the molecule into this program and it automatically show up. Beautiful, isn't it? So now we know the aldehyde proton, the terminal carbon, is highly deshielded. It is at low field, down field, and this signal must represent that. Okay, this position here. So first let's go to the full spectrum, what we see now. Before we do the integration, let's zoom in to the portion that we predict our signal represent the proton. Okay, we go to analysis, click integration, and select the manual way, because we know that this aldehyde proton, there's only one of them. So take note at the toolbar at the top here, it has the same reference integration. You can select from here as well. It's really up to you. So now let's zoom into the signal a bit more, even further. Drone in. Let's do integration now. Integration, click manual, and then again hold and drop your left click. So now this is 1. The first signal that you select using integration, it must be 1. And so now here you see that this doublet represents 1 unit. And if you'd like to change the signal, you can do a right click and edit integral. And you can change the number that says normalized to, let's say, 2.0, and that's worth 2 protons. So now let's change to 2 and we click enter. Now we have number 2. But now because we know the structure that this is only 1 proton, so we just change back to 1. Okay, click and cross. Now let's go back to full spectrum. To the other areas, remember the integration is relative to the first signal that you pick, which is the one we had just now. So the integration again is the total area under the peak, and the number is relative to the first signal that you set. Now the aromatic signal in trans-cinnamaldehyde is about 7.5 area, and we have 5 hydrogens around the benzene ring and 2 in the alkenes. So we expect to see about 7 protons in the environment. Now we select integration and manual and put the mouse over here, and now what do you see now? 2 hydrogens in this zone. Now you see these 2 peaks, they come from the same proton environment, and when we drag over it, it shows a unit of 1 integration. You should know why from the structure. Think about it. Talk to your friends. And for the last doublet of doublet, there might be some impurities here. So on the right side you see there's some bumps and shoulders. That's why we do not have a perfect integer here. So here we got 2.83. So now we can do that for all the signals and get all the protons integration. So with that, we can now verify whether our product here is what we actually want to make in our synthesis. So now let's go back to the full spectrum. So you see now in the full spectrum we have the integration and the chemical shift of all the signals that we are interested in. Now in general, for most of the synthesis, we would have some trace impurities, side products, or even solvent peaks. So if you'd like to find out what they are and how much they are, what is the ratio of your impurities or solvents or whichever against your main product, you can also do integration and check what is the proportion of it. Now, if there's no signal above 10 ppm for your spectrum, you can select the manual zoom function, and horizontal, you can adjust it. Let's change it to 10.0 to -0.5, and this is the step. So see that there are no signals from 0 to 6 ppm, but even so, you do not just truncate this part. You should present everything to us, because this tells us that here you have nothing, which means that you do not have any solvents in this area. And this translates to you have done your purification very well, dry substance accurately, and we're so proud of you. You have to tell us that, if not we won't know, isn't it? Let's raise the peak height a bit more. So here you see the spectrum here is biased on the left hand side because we have more signals there. You can select the expansion window, and after you click on this icon, you move it to the right hand side where there's more space, and put your cursor there, hold your left mouse, and what happens now? A snapshot pops out. Click on this small window, snapshot, and drag to the right side and show us that indeed that it is a quartet, or is it a double doublet? And you still can raise the height of this snapshot. Okay, you can go to the manual zoom, and in this small window, to the right click here, and I can narrow it down. I do not need the other part here. So now we key in 6.8 to 6.65, and voila, what do you see? It's a better view, right? And we can resize the width of the snapshot. And if you're not interested to have peak picking or integration in this snapshot, you can do a right click and go to property, watch this, or double left click is fine, same thing, property. So we go to integration and unselect the integrals. Alright, because it's here, it's present in the main picture, so we do not have to replicate our steps again. Now let's do the same for other peaks. We do a snapshot, okay, so that we can see clearly what they are. Multiplet, duplet, triplet, quartet, pentet. Okay? Alright. So if you do not want to use the same function for your left mouse click, you can click on the same icon again to unselect the function. Put them together. Now you can see the splitting very clearly. No objection to that. Okay, let's key in some values. Let's try a 7.7. Let's try a 7.65 and 7.35. Let's narrow down. Okay, it's broader. Isn't it much better? Don't you agree with me? So in this product that we got, it's a very clean product. But from time to time, in case there are some presence of the CDCl3 that contains some water because it's open to the air for a long time, we might see some signal coming from water, and about this zone here, about 1.5 ppm. So once you're ready to present and submit homework for us, submission, you can click on the icon, export the PDF, and select a folder that you would like to export your PDF file. So here for me, we use trans-cinnamaldehyde as my file name and click save. Okay, and it's done. How do we check? We go back to the same folder that I saved my work, and you see now, it's present. Open out, it's a PDF file you can print. How lovely is it? So now let's go back to the MestreNova software. You can save the file as well. That means what you have done for your work, your integration work, your analysis. It will be under MestreNova file. So we save, and after you close the program, and next time when you come back again, you can still do some more editing. Let's say you forgot to analyze the integration of one of the peaks, or you like to take away some of the signals there. In terms of the numbers, you only change decimal places of the chemical shift. You can come back again to do more analysis and export again as a PDF. It's really up to you. You can even change the color of the fonts, the spectrum. You can feel free to play around with this. Okay? Just try to impress us if you wish to. Follow this guideline and I hope that you can practice more and do well. Thank you very much. Students, have a nice day. I'll see you soon.